for Brownian motion. And we will start from the formulation of the theorem and also from the developing of some intuition how actually the rate function for Brownian motion should look like. It is 7.1. It's Schilder theorem. And before we will formulate the large deviation principle for Brownian motion, I would like to start from the discussion what is that the rate deviation principle for finite dimensional distributions of the Brownian motion, and then having that large deviation principle and having the rate function for LDP for finite dimensional distributions, we will try to predict what the rate function for the Brownian motion itself should be. And after that, we will formulate the statement, and then we will prove it. Then we will start from the notation. We assume that W is the Brownian motion of denote a standard Brownian motion. Standard Brownian motion, it means that the Brownian motion starts from 0 and its diffusion rate is equal to t, or variance of Wt is equal to t. And then we take the partition uh, 0, that is t0 is less than t1, and so on up to td, that is equal to capital T, and consider the random vector obtained from the Brownian motion. It is just W of t1 and so on up to wtd. And it is a random vector, of course, in RD. And then we want to formulate the large deviation principle. Now we already learned something. For instance, we know how we can obtain the large deviation principle for empirical distributions. So therefore, let's consider an independent copies of that vector and write the empirical mean. Let psi1, psi2, and so on be independent copies. Of psi. It means that they vectors are independent and have the same distribution as the random variable psi. And then set or consider the empirical mean that is 1 over n, the sum k from 1 to n, say k. And so since you sum independent Gaussian distributed random vectors, and then you divide it by 1 over n, of course, so this or the distribution of that vector that we obtained coincides solution of 1 over n Sn coincides with the distribution of 1 over square root n, and then you have Wt1 and so on Wtd. It is the simple reason because the expectation, you know that the sum of independent random normal distributed random variable, it's again a normal distributed random variable. When you multiply it by a constant, you also get a normal distributed random variable. Everything what you need to figure out, what is the covariance and the mean. But mean of z vector, it is 0 because the mean of the Brownian motion is equal to 0. And then you just need to compute the covariance. But when you consider z vector, you will have just sum of n covariances, and then you need to multiply it by 1 over n to the square, because you know when you compute the variance or covariance, you can move constant away with square. So, and when you do the same, then you will see the same covariance. It is the reason why both vectors have the same distribution. So therefore, it doesn't matter what you consider for large deviation principle. Thus, either you consider 1 over n as n, and you consider this 1 over square root n w, so this family, and you consider z vector, satisfy the same large deviation principle in RT with the same rate function, because you know that in the definition of large deviation we use only the distribution of random variables. So therefore later it doesn't matter whether we will consider z1 or we will consider z vector. Why I started from the empirical mean here, but not directly from z vector, and here the reason is that we know what the large deviation principle for empirical mean is, because we already proved that we proved in one-dimensional case and discussed it for multi-dimensional case the Kramer theorem, which gives us the answer what is the rate function for and claims that this vector satisfies, or this family satisfies the large deviation principle. Then just let's recall that. So then by Kramer theorem, we have that 1 over square root n of wt1 and so on wtd satisfies the large deviation principle in RD with the rate function with the rate function that is defined by that is the Fenhill-Legendre transform of the vector xi, right, where xi, it is a distribution, it is the distribution of one random variable here, or the same as the distribution of that. So actually, so we get that this vector or that one satisfies the large deviation principle with Fenhill-Legendre transform associated with the distribution, with the finite dimensional distribution of the Brownian motion. And now we would like to precisely see what is a Fenhill-Legendre transform for that distribution. And here we can either use the properties of and the definition of Fenhill-Legendre transform, cumulant generating function, and so on to compute so this one, or we can use its properties. So here I want to use its properties, and so namely, I want to first of all note that finite dimensional distributions of Brownian motion can be obtained as a linear transformation of the distribution of a vector with a standard Gaussian distribution. Let me be more precise. And so let's consider, or write, we remark that when we consider the vector eta, that is, we take wt1 and then we divide by square root t1. And then we consider the increments, wt2 minus wt1 divided by square root of t1 minus t2 minus t1, and so on up to wtd minus wtd minus 1 divided by square root td minus td minus 1. And what we know about that vector, we know that every coordinate has a normal distribution with parameters 0 and 1. And since the Brownian motion has independent increments, all vectors here are independent. So therefore, it implies that the vector eta has the normal distribution with parameters. So it has the standard normal distribution, expectation 0, and the covariance is identity matrix. And also, let's note that so let's or we know that the Fenhill-Legendre transform of this vector eta, we already know what it is because we find the large deviation principle, or we discussed already the large deviation principle for empirical distribution of the standard Gaussian vectors. And we know that the rate function, it is the norm x, the Euclidean norm x squared divided by 2. And now let's also note that, and of course it is trivial to see that you can write eta as some matrix, and you can also precisely compute that matrix. I don't want to do that today. You can do that by yourself as as a matrix multiplied by the vector t1 and so on wtd. Or in other words, in our notations, it is a linear transformation of the vector xi. And also, the matrix A is some non-singular matrix or invertible matrix. And A is some non-singular matrix. And now we want to use the property of Fenhill-Legendre transform that you got that property as an exercise as an homework exercise, and you know that if you have the Fenhill-Legendre transform of the linear transformation, so actually this xi, so here it implies that xi it is a minus 1 of atom. So therefore, you have that the Fenhill-Legendre transform of a minus 1 of eta of x. And by the properties, you know that it is phi star of eta ax. So therefore, it is the norm of ax squared divided by 2. And here you can now easily compute that norm because you see that when you take the linear transformation of ZA and you apply it to vector x, it is the same. So you can be computed it as follows. It is the same as A applied to that vector, right? So it is this vector, but now only you just need to take that coordinates and replace by x. So therefore you will have x1 divided by square root t1, you will have x2 minus x1 divided by z square root, and so on. So therefore, it is here, and you also need to, let me first of all write that, it is x1 divided by square root t1, x2 minus x1 divided by square root t2 minus t1, and so on. Xd minus xd minus 1 divided by square root td minus 1. And then you compute the norm square and you divide it by 2. And you know that the Euclidean norm, it is the sum of coordinates square. you will have sum k from 1 to d, so here 1 over 2 also, and then you have xk minus 1 square divided by tk minus tk minus 1, where we also, for convenience, took x0 is equal to 0. So let's note, or let's summarize what we obtained. We have obtained that 1 over square root n w of t1 and so on, w of td, that has the same distribution as 1 over n Sn. I just mean so writing has the same distribution. I mean that for every fixed n, it has the same distribution. Probably I should not write that. Satisfies the large deviation principle in RD with the rate function, which we computed indirectly, just using the properties and the fact that we know what is a Fenchel-Legendre transform for the normal standard normal distribution, is given as 1 over 2 the sum k from 1 to d xk minus 1 square divided by tk minus tk minus 1. Okay, so, and now we want to understand what should be the large deviation principle for the complete path. Now, instead of z vectors that we considered at fixed times, we want to consider the complete path in the space of continuous functions. And then we want to ask ourselves, what is the large deviation principle and how looks the rate function in that case. And now, having the rate function for finite dimensional distribution, we actually can predict what the rate function should be. And let's do that prediction, and then after that we will formulate the large deviation principle. You see that if you take the rate function at point x here, then it is given by that form. But now we want to take some function f. Now we want to consider to obtain or to understand what is the rate function I for now not only that like a finite dimensional distribution, but the complete path of Brownian motion of this family in the space of continuous functions. Right, because of your paths are elements, or your Brownian motion takes values in the space of continuous functions as a map from omega to its trajectory w of omega. So therefore, your rate function also should depends on that. Should depends also on the continuous functions. And let's consider some function. Probably here also, let me see how we are. I should make also that the remark that we actually should not consider all the space of continuous functions. We only can consider continuous functions that starts from 0. So let me put here 0 and also say where C0 of 0t, it is the continuous function f from 0t to r such that so, or maybe it's better to write that as follows. It is continuous, and f of 0 is equal to 0. So the space of continuous functions started from 0. Okay, let's take the function. So it is a function f. So it is up to time t. It is a function f. And let's note that the previous rate function, which is written here, it was also, we can rewrite it as follows. So look, what we did before, we fixed it sometimes. It was time t1, here was probably t2, t3, and so on. And then we considered our Brownian motion at that times. So therefore, this value here, it is the value of function f of t1. And your x2, and it is your x1. So x1, it was f of t1, x2, it is f of t2, and so on. Right? So therefore, when you just change the notations here in that formula, what you will see? You will see that probably the rate function I of f, it should be something like, okay, at least for finite times, we obtained 1 over 2 the sum f of tk plus 1 minus f of, let me check, tk minus 1, tk minus 1, divided to the square, divided by square root tk minus tk minus 1. But what does it is? So it is just please wait a second. We need to
Maybe
make.
we don't need the square of t minus tk minus 1.
It should be just t minus 1 probably. Let me see. It has to be t minus 1. Right. And to wait 1 second, I will need. Okay, Katya will need to delete that part with the interruption. So, okay, so let's continue. But now you want to understand, okay, what happens with that function in the right hand side when you make like when you take more and more times here and you consider like I mean when you send n to infinity or make a finer and finer partition. And at the moment you cannot see what the limit is, but I want to do a small modification of that part, and I want to write here, just here put square and then multiply by. So I actually did nothing. I just multiplied and divide by tk minus tk minus 1. And now you see that this that this part here, it looks as the derivative of the function f and at say tk, and then you multiply by increments, that is say delta tk. So you see precisely the Riemann sum. So from that one, you should expect that your rate function for the large deviation principle for Brownian motion has the following form. It is 2 integral from 0 to t f prime of square of t square dt. And just in a few minutes, you will see that indeed it is exactly the rate function for the Brownian motion. And Brownian motion satisfies the large deviation principle with this rate function. Now I want to formulate the theorem. This theorem of 7.1 in lecture notes. It is Schilder's theorem. theorem, which says that that the family. Also, let me make a remark that for us it will be more convenient to replace this 1 over square root n by square root epsilon, and assume that this epsilon just is a positive number. So therefore, let me write that as follows. So the family square root epsilon w, epsilon larger than 0, satisfies the large deviation principle in the space of continuous functions on 0t started from 0 with good rate function I of f is equal to 1 over 2 integral from 0 to t f f dot square. I will explain what it is because here we need to be now very precise. If f belongs to h0 to 0t and plus infinity otherwise. When h0 square 0t is the set of absolutely continuous functions say h from c0 0t with that its derivative belonging to L0 0t. So I mean with the derivative which is integrable. Recall that just recall. Maybe we will write by that corollary that recall that that every function what means that the function is absolutely continuous. Now the function starts from 0, so therefore it means that you have actually h of 0, that in our case it is 0 plus integral from 0 to t h dot of s ds for some that let me write that better, more carefully. So recall that h is absolutely continuous. If there exists a function h dot from L1 0t such that you can write that function h of at time t, it is that h of 0 plus integral from 0 to t h dot of s ds. And also it is not complicated to see that this function is almost everywhere unique. So if you have another function satisfying that expression, then this function, then both functions are almost everywhere unique. Also, it's easy to see if the function h is continuously differentiable, then this function is exactly its derivative. But also it can happen that function is not continuously differentiable, but still you have that expression. And so such a function we call it the absolutely continuous function. And in this space are not only absolutely continuous functions, but functions that start from 0. And this derivative is a square integral. Okay, I hope that the definition of rate function is clear for you. Also, this rate function you saw before, because you also got some homework exercise where you had to show that this function is lower semi-continuous. It is also good function. And now you see that function as a rate function for large deviation principle for Brownian motion. Okay, good. And now we want to prove that theorem. And you should remember that we already discussed it with you that to be able to prove the lower bound in the large deviation principle, you just actually need to work with the probabilities that your random objects belong to some balls, and then estimate that probabilities from below. For upper bound, it is not enough to work with only with balls, but working with balls, you can get the weak large deviation principle. And then to get the full large deviation principle, you need to obtain the exponential tightness. So therefore, our strategy will be the following. We will estimate the probabilities related with balls. Then we will obtain the weak large deviation principle. And after that, we will show that we have exponential tightness for this family of Brownian motions that will guarantee the large deviation principle, or that will guarantee the full large deviation principle. And since we need to care about the probability, so let me write that here, that we need to estimate the probabilities that Brownian motion. Let me also denote that Brownian motion, which is here by W epsilon. Which the probability is W epsilon belongs to the ball of radius r at center F. So actually, it is a probability that Brownian motion W epsilon minus F is in the uniform norm less than R. So bam. This W epsilon, as I said, it is square root W. And to be able to work with or estimate that probabilities, we need to work with this shift of the Brownian motion. So therefore, we need to better understand what the shift of the Brownian motion is, or how we actually can work with that. So therefore, we first have to make some preparation, and we will do that in the next section. It is the section number 7.2, Cameron-Martin formula. Actually, our idea will be the following. Our idea will be that, okay, instead of working of this shift of Brownian motion, we want to replace the probability space by such a way that this shift will become a Brownian motion. And to be able to realize that and give you and formulate the precise statement, I would like to give you before some intuition what actually we will do. So therefore, I just propose you forget for a few minutes about the Brownian motion and consider a very simple situation. Let's assume that we have a random variable and that has a normal distribution with expectation 0 and variance 1. It is a random variable in R. Just one-dimensional case, and define it. So B define it on a probability space. Omega Fp. And also let's take a constant A that belongs to R. Then what we can say about eta minus A? Eta minus A, it has a normal distribution with parameter A, comma 1. Because you know when you add some constant or subtract some constant from the normal distributed random variable, it's again normal distributed random variable. and with the corresponding mean and variance. But when you shift a random variable, mean also is shifted, but variance is not changed. So therefore, it is the reason why it is a normal distribution with parameters a and 1. And now our idea is the following, that it turns out that we can change our probability space by such a way that this object has a standard normal distribution. Now, let me show how we can do that. So now let's define, or let's consider a new distribution which we define as follows. We put here A, and on the set A, we define it as an expectation of the indicator A of e to the power a eta minus a squared divided by 2 for every a belonging to F. And now we consider eta on the probability space omega F, but we change now the probability measure. Then it turns out then eta has a normal distribution with parameters 0 and 1. So be careful. So here it is 0 and 1, but you see before, with respect to the old distribution, P, it has the expectation, it has the expectation A, but now when you shifted it and changed the probability measure by a special way, you obtain it, oops, I'm sorry, I wrote something stupid. You obtain that eta minus A has a normal distribution with parameters 0 and 1. So indeed, let me show that it is indeed so. Here is no magic. Here is just straightforward computations. Because how you can figure out what the distribution is? You just need to compute that the distribution function and show that it's coincide with the distribution function for the standard normal distributed random variable. So let's take eta minus a less or equal than z. Then it is equal to that according to our definition here, that you need to take that the expectation of indicator of that set a minus event a eta minus a less or equal than z multiplied by e to the power eta minus a squared divided by 2. By the way, I forgot to tell you, when you consider this new measure, it is easy to see that it is indeed the probability measure. When you take a is equal to omega, then put here omega, then your indicator is equal to 1. You can remove it, and then you can precisely see, you can easily see that expectation is equal to 1. So you have, by this change, you also have the probability measure. And then computing that, you know that expectation can be computed as follows. It is just the integral of that function that you have here multiplied by density of eta. You have the indicator of x minus a is less or equal than z, e to the power ax minus a squared divided by 2, and then you multiply by the distribution of by the density of normal distribution. It is 1 over square root 2 pi e to the power minus x squared divided by 2 dx. And then let's continue the computation. It is this indicator gives you that you need to integrate x, you need to integrate from minus infinity to z plus a e to the power, and then you will have that constant 1 over 2 pi that you can put outside, and inside you will have the following. You will have minus x squared divided by 2 plus ax minus a squared divided by 2 dx, and then when you continue that, you have here z plus a e to the power minus x minus a squared divided by 2. And then when you shift the variables, you can put here plus, you can put here minus a, and you replace z by y. You will have here also y, and then you also need to shift that point. And when it's just changing the variables, you will obtain 1 over square root 2 pi integral from minus infinity to z e minus y squared divided by 2 dx. That is exactly the probability, but the old probability of eta less or equal than z. So that implies that eta minus a has a normal distribution 0, 1, but on this another probability space. And then it turns out that we can do the same trick for the Brownian motion. But now, of course, you need to like work a little bit harder than we work it here and define a little bit more complicated object. But actually, it gives you a good intuition what you should write and what actually you should expect. And that result in the literature is known as as a Cameron-Martin formula, which we will formulate it now. So let's consider let W with sigma square of t be a Brownian motion started from 0 and diffusion rate sigma square. What does it mean? It means that the variance of W sigma square t it is sigma square t for every t. And then we introduce then for h that is a square integrable function. We define also the transformation of the measure. We before defined it for constant a. Now we have the function that is defined as follows. It is as before. Expectation indicator of a, but here your density is defined by the integral, by the stochastic integral. It is integral from 0 to t h of t d Brownian motion. You integrate with respect to Brownian motion, and then you write minus sigma square divided by 2 and then quadratic variation h square of t dt. And you also do that for every a from your sigma algebra f. Maybe also it makes sense here to specify that this Brownian motion, I didn't wrote that define it on the probability space omega fp. So once again, you have Brownian motion, diffusion rate is sigma square, it is defined on the probability space, which we denote by omega fp. And then we took some function which is integrable, and then we defined that measures, that probability measure. You can indeed show that this is a probability measure of one can show the pH of omega is equal to 1. For instance, you can use the Ito formula to show that. But the Cameron-Martin formula says the following. So it is, I formulate that as a proposition. 7.4. Let let W sigma square, this pH and comma H be as before. Then the process W sigma square t minus sigma square integral from 0 to t h of s ds is a Brownian motion motion with also started from 0 with diffusion rate sigma square. The same as in that case, you see that we did the shift and the variance was not changed. So therefore, also in that case, the variance is not changed. The diffusion rate is sigma square, but now this shifted process is a Brownian motion on the probability space omega f and then ph. And now it is a way how we can work with balls to prove the large deviation principle. Because we change in the probability space, we will go from the shifted Brownian motion to the Brownian motion itself. But then we need to work, or somehow we need to work with different probability which we will estimate. Okay. Now we are ready to start the proof of large deviation principle for Brownian motion. 7.3 proof of Schilder's theorem. And we will start from the proof of, as I already said, proof of weak large deviation principle for Brownian motion. It is 731 proof of weak large deviation principle for Brownian motion. And let me recall that that W epsilon, it is square root epsilon W, where W is a standard. Let's write that more precisely. Is a standard Brownian motion. Defined on omega fp. And now we want to show, first of all, the lower bound of V. We start from the lower bound. What does it mean? It means that the limit, the lower limit or lim inf epsilon goes to 0. Epsilon logarithm the probability that W epsilon belongs to open set is larger or equal than minus infimum over this open set of the rate function I for each open set G. That is a subset of the space C0T. Our metric space, it will be that space of continuous functions started from 0. And to prove the lower bound, we will use the proposition 3.5. We will use proposition 3.5, which we already discussed and proved, and it says the following. Actually, that proposition says that instead of proving of the lower bound for open sets, you need to prove the lower bound only for balls. Let me formulate that more precisely. We need to show that that first, for every, and we don't need to consider balls with centers at every point of the metric space. We just can take only balls with centers from this quite large set. And this large set, it will be the set of twice continuously differentiable function. For f, it is from, we denote that by E0, but now it is a space of continuous functions that have continuous second derivative and also start from 0. So we obtain, so that for that functions, we have that limit. Radius goes to 0. The lower limit, epsilon goes to 0. Epsilon logarithm, the probability that W epsilon belongs to the ball is larger or equal than minus I of f, when let's recall that the I of f, it is defined as 1 over 2 the integral from 0 to t f dot square of s ds or t dt. If f is absolutely continuous with square integrable derivative h dot and plus infinity otherwise. And the second, this set E0, that is in our case the space of continuous function, 2 times continuously differentiable functions, has to be large enough. That means that for every f for which this rate function is finite, so for every f such that rate function of f is finite. So actually, it is equivalent that f belongs to h0 to 0t, right? We have that there exists a sequence fn from C0, from this set to which we restricted our inequality, I mean, so from that one, such that we have that fn converges to f in C0, 0t, and I of fn converge to I of f. I want to say that the second part, this one, it will be as a homework for you. 2 is an exercise for you. That actually you can approximate every absolutely continuous function by the functions that are smooth enough by such a way that also the rate function converge. And then we will focus on the first on the first property. Okay, then let's take the proof of 1. So stated in 1, let's take or fix f from C0 t, and also we estimate the probability that the W epsilon belongs to BR of f. That is the probability, the norm of W epsilon minus f less or equal than strictly less than r. And we estimate this probability from below. And now, so we will use the Cameron-Martin formula. And let's go back. And here you see that in the Cameron-Martin formula, you have that you consider the Brownian motion with diffusion rate sigma square. But in our case, we have the Brownian motion with diffusion rate epsilon because we multiply it by square root epsilon. So our sigma square, it is epsilon. And then you have the function f. So therefore, your function h, it has to be the derivative of the function f. Let's define or take h that is equal to f prime. And consider the following measure. We will denote that a little bit differently because it depends on h and also epsilon of a that is equal to the expectation of indicator a e to the power integral from 0 to t h of t divided by epsilon dw epsilon of t and then minus epsilon square, epsilon divided by 2. So it is diffusion rate, epsilon divided by 2. But our function actually here, it is not h, but h divided by epsilon. I will explain you the reason in a moment. So therefore here epsilon square dt. And then you can continue that, just move that epsilon outside. You see that it is expectation, indicator A, 1 over epsilon. And then you have the integral from 0 to t, h t dw epsilon of t minus, and then you will have 1 over 2 integral from 0 to t, h square of t dt. And then note that then the process W epsilon, you can see the Brownian motion with diffusion rate epsilon, right, minus diffusion rate, that is epsilon, and then integral from 0 to t, the function which you wrote here. It is h of t divided by epsilon, d, we need to write s, and that is w, we have also t, that is w epsilon of t minus integral from 0 to t, h of s ds, that is w epsilon of t minus the function f of t. And that process is a Brownian motion on the probability space omega f and then p h epsilon. So therefore, if you can replace this probability by the new probability, by that one probability, then what you will see? You will see just the probability that your Brownian motion, the norm of Brownian motion is less than r. You will not see anymore that function f, which is here. And actually, it is our idea to estimate that probability. First of all, we will before we will make that estimates. I would like to consider the term which we have here more precisely, because here you have the function h that is first of all deterministic function. That function is continuous because it is just the first derivative of your 2 times continuously differentiable function f. And also this function is continuously differentiable because it should be the second derivative of f. So therefore this stochastic integral you can rewrite as a usual Riemann integral, and it will be convenient for us to do that, like to rewrite it via the Riemann integral just by integration by parts. Let's note that the integral from 0 to t h t dw epsilon t minus the 1 over 2, the integral from 0 to t, you can h square t dt. You can just in the first integral, and I'm sure that you know that if you know the integration by parts formula for stochastic integral. If not, then you can just prove that directly using the definition of the Riemann integral and just repeating the usual integration, the proof of integration by parts formula. You will see that it is, you will say have h of t w of t, then you need to write h of 0 w of 0, but it is 0. I will omit that, and then you will have minus integral from 0 to t h prime of t w epsilon of t dt, and then minus 1 over 2 the integral from 0 to t h square of t dt. And this form of writing that, so that expression is more convenient for us because you can see that actually this is a function of the function h and the function epsilon, w epsilon. And moreover, it is a continuous function as a function of h, as it is a continuous function as a function of w epsilon. Because you see, you don't need to anymore integrate with respect to w. Your w is here, is inside the integral. And now having this new notation and that observation, let's start the estimate. Let's write the probability that w epsilon belongs to the ball. It is, we want to go to the new probability. So therefore, first of all, let me write that as an expectation of indicator that w epsilon, but actually it is the norm, maybe I will write w epsilon belongs to br of f. And now I want to multiply by e to the power 1 over epsilon and that in that expression. And then I need to divide by it. Or I can write that as follows. And now we can estimate, and now I want to say that this part here, it is exactly as that part. So exactly as in this distribution. You also have the indicator, it is an indicator here, and only you need to do something with that expectation, and then we will estimate. We will just estimate it by supreme. No, by infimum. We want to estimate from below, we will estimate by infimum. It is smaller or equal than the expectation of indicator w epsilon belongs to brf multiplied by 1 over epsilon v h w epsilon. And then you need to write here the infimum. And you see that your randomness, that function is fixed. Only you have randomness here. So, and here you take this w epsilon belonging to the ball. So therefore you can estimate that by the infimum of over function g belonging to the ball of radius f and center epsilon. And then you can put here e to the power minus 1 over epsilon phi of h comma g. By the way, let's note that this function f, it is well defined not only for path of Brownian motion, as you can see here, but because of that equality, it is well defined for any continuous function. So therefore, we just estimated this one by the infimum and replacing the Brownian motion by the function g. And then we can continue. It is just using the monotonicity of the expectation. You will have the expectation of indicator epsilon belongs to br of f. And then you have e1 over epsilon v h w epsilon. And then you will have e, you can move that everything outside. And then you will see here e to the power minus 1 over, you will see infimum, but then changing infimum and minus, you will get supremum. So therefore you will have 1 over epsilon supremum. G belongs to brf of the function phi h g. And then let's continue. And it is the new probability h epsilon of the Brownian motion w epsilon minus f is c is less than r multiply by e to the power 1 minus 1 over epsilon supremum over, so g belongs to br of f phi h comma g. And let's note that by the Cameron-Martin formula, this is the usual probability. Let's note that this is the Brownian motion. Brownian motion. So therefore, you can write. I will just copy that part. We'll go to new page, and we'll say that we estimated that by that probability that Brownian motion, it is a probability that usual Brownian motion with diffusion rate epsilon is in that supremum norm is less than r. You have it will be more convenient for me to write that as follows: epsilon w c is less than r, and then you multiply by that exponent, which I will just copy. You have that exponent. But now also I want to note that okay, let's just continue. And now we want to in one we want to consider that expression, and then we want to consider the limit when epsilon goes to 0 and then r goes to 0. Let me write that. Then limit r goes to 0, lim epsilon goes to 0, the lower limit, epsilon logarithm the probability of w epsilon belongs to brf. You will have that it is larger or equal, and then you need to, so we estimated that from below by lim r goes to 0, limit epsilon goes to 0, epsilon logarithm the probability, and then you have the probability that norm of square root epsilon w c is less than r. But if you like, I can write that r divided by square root epsilon, and then you will have multiplied by e to the power minus 1 over epsilon supreme over the ball. And then, okay. And then using the properties of probability, you can see that you can split that logarithm on sum of two logarithms. You will have epsilon logarithm the probability. And then you will have here plus epsilon logarithm of the expectation minus 1 over epsilon supreme. And then you see that, look, what happens with the first expression, with that probability. That probability, it goes to 1. Because when you send epsilon to 0, this term here goes to infinity. And then you consider the probability that the supremo Brownian motion is less than infinity. That is equal to 1 in the limit. So therefore you have epsilon going to 0, and logarithm 1, it is also 0. So therefore this term here, it goes to 0. But this term here, logarithm and expectation disappear, and epsilon also disappear. So therefore, you can see, I can move minus outside. You can see limit. R goes to 0. And then you see supremum over G belonging to BR of F, the function phi of H comma G. And now let's note that you take the supremum of the function which is continuous with respect to this slot, the second slot, over the ball. And then you make the radius of the ball going to 0. So therefore, it is not complicated to see that this limit, it is exactly minus phi of f comma of h comma f. But let's compute what it is here. And you see that, so let me see whether I didn't skip sign minus nowhere. It seems that everything is okay. Okay, it is minus phi. And let's continue. It is equal to once again the function phi. It is defined like that. And we just need to just take that formula and just replace w by the function f. You will have it is equal to minus, and then you have, let me just copy that, or maybe separately I will compute that function here. You have the function phi h of f, it is equal to. Then without minus, we can just copy that function which we defined here. I do not remember it. And you need to replace w by f. Let's do that. It's f of t. It is f of t. And it is, okay, no f of t. It is equal to we just integrate by parts once again. What we do, we just take that h and move it inside that determinant. We will have h of t, f of t minus, and then it is integral from 0 to t h. I'm sorry, it is f. It is f of t dh of t, and then minus 1 over 2 integral from 0 to t h square of t dt, and then it is equal to h t f t, and then you will have minus, and then f of t h of t, and then plus integral from 0 to t h of t f prime of t minus 1 over 2 integral from 0 to t, and it is h square of t dt. And now, so that disappear. And now let's recall that h, it is f prime. So then you will have integral from 0 to t, f prime of t square dt minus 1 over 2 integral from 0 to t, f prime of t square dt, that is equal to 1 over 2 integral from 0 to t, f square prime t square dt, that is exactly the rate function of I of f. And what did we obtain here? We obtained here that just after the computation, we obtained that this is minus, and then you see the rate function I of f. And let's go to that to the statement or to that property, the first property, and exactly you want to see minus that minus rate function at f. of this this finishes the proof of the lower bound. So this implies that we have the lower bound. Okay, good. And now we want to obtain the upper bound, but let me check. Much time do I have? Okay, now for upper bound, then proof of upper bound for weak large deviation principle. And for the proof of upper bound, we already discussed that it is enough to show that we can control only the probabilities for balls. That for every f that belongs to C0, 0t, we have that the limit r goes to 0, lim epsilon goes to 0, the upper limit of epsilon logarithm, the probability w epsilon belongs to the ball of radius r with center f is less or equal than minus I of f. And then we will also repeat the same computations. You remember that maybe also I can not only, repeat, I will just copy what I had here. Let me copy these estimates and somehow modify it. Copy. And now to obtain that inequality, like do the following. So we consider now an arbitrary function h from C10t. In the lower bound, we considered h, it was a derivative of f. But now we don't make that assumption. It is just some function that is continuously differentiable. And then for that function, let's do the computations, which we already, or estimate, which we already did. But we wrote the estimate from below. But now we want to write the estimate from above. So you write that probability. You just put E and E here. Then you want to estimate from above. So therefore, you just take that and you replace, maybe I will write by another color to say what is changed. And then here you just put supremum, right? Because you want to estimate that from above. Then you can move supremum inside the expectation using the monotonicity. Therefore, here you have infimum. And then you will have the Brownian motion, you will have infimum. Okay? And then also I want to say that since we write the estimate from above, you see that we can continue that and can write that, okay, it is less or equal. And then this probability here is less or equal than 1. We just can remove it. And you will have e to the power minus 1 over epsilon infimum over the ball. And then you will have phi h of g. So what you did, you just remove the probability. Okay, and then for that function h, then thus for h that belongs to C0t1 and starts from 0, we have no, we don't assume that that function starts from 0. Before it was h, it was a derivative, but now, okay, it is any continuously differentiable function. And then you will have that for this, you have that the limit r goes to 0, upper limit now, of epsilon logarithm, the probability w epsilon belongs to br of f can be estimated by limits r goes to 0, lim epsilon goes to 0, epsilon logarithm, and you have e to the power minus 1 over epsilon. Let me see, it is infimum of the function phi of h comma g. G belongs to the ball. And of course, you see that logarithm and exponents disappear, epsilon, and then as a result, you can see that minus, I just took minus and put outside the limit r goes to 0, and then you have infimum, g belongs to brf, and phi of hg. And the same reason as was for the infimum, that the function capital phi is the continuous function, u and radius of both goes to 0, then that limit, it is exactly minus phi h of f. So this implies that we obtained the upper bound of that for by this one, where the function h, it was any function which was continuously differentiable. But if it happens for every h, it will also be true if you will take the infimum over h. So therefore, this implies that lim r goes to 0, lim epsilon goes to 0, the probability W epsilon belongs to BR of f is less or equal than infimum over all h belonging to C1 0t of minus phi of h comma f. Or it is the same as minus supremum h belongs to C1 0t of phi of h comma f. And next time, our goal will be to show that this supremum here is equal to exactly the rate function I of f. It is our goal. For instance, you know that if the function h is if the function h is that the derivative of this, if this function is 2 times continuously differentiable, and h it is the function that is the first derivative of f, then we showed that this f, it is exactly rate function. But now see what is the difference between the lower bound that we had before and this expression here, that now we take f, it is any continuous function. It is not anymore continuously differentiable function. So therefore, it can happen that you have no derivative of f. And in this case, when you have no derivatives, also it can happen that it is not absolutely continuous. In this case, your rate function must be equal to plus infinity. So therefore, this situation here, it is more complicated because you need to pay an attention that f, it could be any continuous function, not necessarily absolutely continuous or 2 times continuously differentiable. And anyway, when you take supremum over the function h that are continuously differentiable, this expression here, so I mean this object here, it will be exactly the rate function. We will need to work with some special estimations, with some variational problem, because we need to investigate this function on the supremum. We need to show that supremum is exactly that one, but it will take some time. We will need to use a little bit functional analysis to compute that supremum, and then we will come to the consequence that it is a rate function. After we will do that, it will be done next time. We will discuss the exponential tightness of the Brownian motion, and then the weak large deviation principle will apply the full large deviation principle. Okay, it is everything for today. Thank you so much for your attention.